All right, let's get started. Thank you all for joining this session. It's my second time at KCD UK. I'm very happy to be here again. So I hope you're comfortable on your seats because this afternoon we're going to go on a nice journey. We are going to take the helm, pun intended, and we are going to navigate what it means to run Helm at a very big scale, dealing with 1,000 Helm releases per day. So we're going to go through what it means, what are the differences between running Helm on a small scale and running Helm on big clusters, big infrastructures. We're going to go through the bottlenecks, the challenges, the mistakes that we did, and the lessons that we learned so that hopefully you will not make the same mistakes, whether you are scaling up your infrastructure or you're just pushing the boundaries. But let me introduce myself first. So my name is Giorgia. You can call me Jo. This is me. You see these pictures, and you might think, oh, wow, she's an adrenaline junkie. Look at that, surfing, skydiving, public speaking. Truth is, I'm not. It's just a pretend. I just say yes one too many times. So besides that, I am a cloud reliability engineer at Adobe. And I work on a product which is called Adobe Experience Manager. It is an enterprise product, and we help our customers to build their own websites. I am part of the foundation team, and as the name suggests, it helps building and laying the foundation for our product. So we are doing everything that involves cloud operators, Kubernetes, so building the controllers, the operators, managing the releases, managing the upgrades, logging stack, monitoring stack, so on and so forth. And as part of my job, I had a lot to do with Helm. I had the opportunity also in my previous company to deal with Helm on a smaller scale, and now to deal with Helm on such a big scale of a company and of a big product like the one that we are currently dealing with. So let's start. First round of questions. How many of you have used Helm at least once? Okay, perfect. Now, second question. How many of you use Helm on a daily basis? Cool, perfect. Okay, so we can start with a little bit of a warm-up and just refresh what Helm is. So Helm is a templating tool for Kubernetes deployments. It's very handy because it allows us to package our applications through Helm charts. And these allow us to also encapsulate our Kubernetes objects into one single entity that then we can download and we can apply and deploy to our clusters. And this is done thanks to the templates that we can use. We can use these templates to lay down a structure as kind of a skeleton of what we want to deploy, and then we can apply values on top of these templates to customize our deployments, our resources, depending on the environment that we are deploying to. So, just to give a little bit more of an overview, we have our template, which usually is more than one file. And then we have our default values, which are like standard values that usually are also provided in the whole package when we download the Helm chart. And on top of these default values, we apply different sets of values, different sets of overrides, depending on the environment that we are deploying through. In this specific situation, which is very common, we are having overrides for development environment, stage environment, and production environment. And this way we can distinguish these three environments and what we are going to deploy, because maybe, for example, I don't know, we're testing something in the development environment, it's risky, might make something break in the production cluster. And then we use these three different overrides and we deploy to our cloud, to our clusters. But this is what happens on a small environment, on a Minikube cluster, or on a small cluster. But what happens when we're going to scale? So we have our template, we have our default values, but we do not have only three overrides. It depends on how many customers, how many tenants, how many namespaces we're dealing with. So we can have 2, we can have 5. We can have more. I didn't count up to that number. And we have to deal with all of these different overrides, all of these different versions of our application, depending on the tenant, on the namespace, on wherever we are deploying and whatever we are deploying to our cluster. So it's very diversified. Is this enough? Is this close to real life? Not always. It can get a little bit overwhelming, because these are the numbers that we're dealing with. We have 11 regions. We have 50 clusters. We have 12,000 namespaces across 50 clusters, and 30,000 Helm releases. And it can get a little bit hard when we want to ensure continuous delivery, so when we want to make sure that our customers always have their product up to date with all the patches, all the fixes, all the updates that we are delivering, be it their also customizations or be it infrastructure updates. We want to ensure scalability, so we want to make sure that whatever we have can also run at a higher scale. And also, last but not least, reliability, because we need to make sure that everything stays up and running, that we try to prevent incidents, and that we try to prevent any of these situations that can cause customer attrition. And how do we do that? So first off, we need to automate some things in the cluster. So we call the operators to the rescue. We cannot do everything manually. In our specific use case, there are so many different tools that can be used for continuous delivery, continuous integration, and also to deal with Helm. In our use case, we have this story with Flux operators. So in particular, we are using the Helm controller and the source controller from Helm. What are some of the features that they provide us with? So we have multi-source repository support on the source controller side, which in our case, we use to have our Helm repositories downloaded and fetched to our cluster. Then we have, very important, the Helm chart synchronization. So whenever we are pushing updates to our Helm charts and our templates, it is synced automatically as soon as we try to pull a new version of the chart in the cluster. And finally, we have automated release management, meaning that be it the customer or be it us from the infrastructure side, we try to deploy different with a new version, new values in our cluster, everything is managed automatically. So all the values, all the Helm values are updated in an automated way, and we do not need to intervene manually. So this is a very nice chart which was provided by Flux CD. I got it from their GitHub on the Helm controller repository. And these are the resources that we are dealing with and what we need to deploy in our cluster to get everything up and running for our workflow. So first off, let's start with the Helm repository, Helm chart, and Helm release. These are the custom resource definitions that we are going to have in our cluster, which are going to define our Helm objects that we are going to deal with. The Helm repository, the names are quite self-explanatory. The Helm repository is going to provide the coordinates of the Helm repository that we're dealing with, and it's going to be managed by the source controller, which is in charge to, authenticating to the repository, making sure that the artifact is doing the checks and all these kind of things, and then making the artifact available in the cluster. Then we have the Helm chart and the Helm release. So the Helm release is the resource that is applied onto the cluster, which is going to represent the value, besides other configurations, of course, it's going to represent the values that we are going to apply on top of our templates. So in these Helm release objects, we are going to define the values. And as soon as we apply this object onto our Kubernetes cluster, a Helm chart is going to be created, because in the Helm release, we also define the version of the Helm chart we are applying our values to. And once we have this Helm chart, what the Helm controller does, it starts a reconciliation. During the reconciliation, it's the things that we do manually with our Helm. It applies the values on top of the templates. It also applies some customized post renderers. So if we want to tweak some values and we want to have that additional flexibility of tweaking some values that are not included for any kind of edits in our Helm chart, we can do that thanks to the customized post renderers. And then it's going to apply it to the cluster. So it's going to create the resources, the Kubernetes objects that we need. And doing so, we're going to have these resources, the releases, which can be stored either in a secret or in a config map or on external storage. In our specific use case, we are storing these Helm releases, with the release, the versioning, into secrets. But it's all fun and games, because this is just one namespace. But here come the bottlenecks, because it's not always so easy when we're dealing with such an amount, such a number of namespaces. Starting with the Kubernetes API server. So let's get back here. As you can see, the Kubernetes API is taking care of multiple objects. It's watching over the Helm repository, Helm chart, and Helm releases, because these resources need to be watched by the two operators. You have the Helm controller, which is communicating with the Kubernetes API, and also the source controller. And as long as you have just maybe one, a couple of namespaces, this communication works just fine. But when you start increasing, not working anymore? OK, perfect. When you start increasing, it was a slowdown in the deployment. When you start increasing, the API server can start to struggle, because you're going to have multiple namespaces with the Helm controller and the source controller, which is the easiest deployment that you can do of these operators. You just deploy them in your namespace. It's easy on the point of view of the role bindings, the roles, so permissions that you got to have on top of these resources. And you start scaling up, and you have a lot of more other challenges to deal with, and you don't realize that you're literally replicating this controller in every single namespace that you have. And at some point, it just cracks. You can have problems. The API server can get overwhelmed by all these requests, which are redundant, because they're all the same controllers, which are replicated in every namespace. So the solution here, and this is my first tip for you today, is to centralize, and do that as soon as possible. Because, as I said, when you start scaling up, and you start from a small infrastructure maybe, you have other priorities, and you start deploying. Maybe you want to speed up your deployment, and the easiest thing to do is to deploy everything in every single namespace, and you see everything is working out, so you keep deploying. But when you scale up a lot, it doesn't work anymore. So how do we centralize with the Flux operators? We use the sharding capability. So the sharding capability is a feature that was introduced recently. I don't know how much, maybe a few years ago, not so recently. It's a feature that was introduced in the Flux operators that allow us to centralize the operators and have different shards, so different, I wouldn't say replicas because they're not replicas, but different shards of the operators that are watching over a set of the namespaces. So it's not replicas, it's different deployments. So we can start with Helm controller and source controller, one shard in one centralized namespace. And these two shards, which are flags that are defined inside of the deployment of the controllers, are going to tell the two controllers that they need to watch over all the namespaces, only those namespaces that contain resources which are labeled with shard 1. And you keep doing it. You keep deploying different. You keep having and adding different deployments. So you're going to have shard 2 and shard 2, which are going to watch over a second set of namespaces, which is going to have a sharding label, which is going to be shard 2. And finally, you can add as many shards as you want. Just be aware that they're, of course, using resources. So, and you are centralizing, so you cannot use the same amount of resources that you're using on a namespace level, because they're going to deal with a lot more reconciliations and a lot more resources. But in our specific use case, let's say we have on average 250 to 300 namespaces per cluster, which were running Helm controller and source controller on namespace level. And we started having some struggles at some point, because the API server, when all these controllers are continuously, maybe are on a high load, on a high level traffic because of some upgrade or some specific event, they started overloading the API server until it stopped responding. And we went from, if you do some quick maths, around 600, from 500 to 600 controllers per cluster to just 20, because we deployed 10 Helm controllers and 10 source controllers on a centralized namespace. And this is a sneak peek of what happened. So these two dashboards show the exact moment where we rolled out the cluster-wide controllers in one of our clusters. And you can really see here how both the total request count and the request per second dropped. We went from around 8 million requests in the request count hourly to 4 million, around 4 million. So it's almost half less requests. And as we can see, also the requests per second, besides becoming also a little bit more stable, they also dropped to 40% less, from around 2K requests per second to a bit more than 1K requests per second. But that's not the only advantage, because centralizing also enables better scheduling. This means that also the Helm reconciliation, so the time that the controller take to apply, to do all the Helm operations and apply the deployment onto the cluster, is faster. So we're dealing with 2.5 times faster in the P50, so in the median. And as you can see from the second graph, it's significantly more stable. That is the P95. So as you can see from the P95, what were the outliers and how slow some Helm reconciliations were going, and how we improved the stability of our system just by centralizing the Helm and the source controllers. This is not the only bottleneck, though, because we also have a bottleneck in the etcd storage. Let's take a look. Back to this graph, we can see here that we are creating these releases, these resources here. These are secrets. The amount of these resources that you're going to create depends on a value that you set in the Helm release, and it's the value of the size of the Helm history. The Helm history is fundamental because it allows us to have rollbacks, and it allows us to have versioning in our clusters. So it's not something that we want to get rid of. But same, when we have just a few namespaces in a very small cluster, just a few namespaces, we keep storing our Helm releases, our releases, our secrets, and we don't really mind of the size. I mean, we do mind, but a little bit less. And then we keep increasing, and we keep adding more and more namespace without being mindful of editing, of changing that number, of changing the size of the Helm history. And at some point, you wake up one day, and your etcd storage is read-only in your cluster. And you cannot store these secrets anymore, but it's not just about the secrets, it's just about all the resources that you are storing in the key value store of your Kubernetes cluster. So what do you do here? You declutter. You start doing some decluttering, you start doing some cleanup. And you want to be mindful of the amount of resources, of the amount of secrets and config maps that you are saving in your cluster. So you start from here, and you say, OK, I have different kind of environments, different kind of namespaces. What can I do? You start reducing the Helm history. It's a parameter that you can set in your Helm release. In the case of Flux, it's a parameter you can set in the Helm release object. And you start reducing, and it doesn't have to be the same. You can store longer history or shorter history depending on the use case, depending on the kind of environment, on the kind of namespace that you're dealing with. In production, you might want to have a longer Helm history just to make sure that you have longer versioning and that you can roll back further releases. While, for example, in stage environments or in development environments, testing environments, we might not want to have that long of a history because we don't really need that. If it's just a testing environment, RDE environment, we also might keep just the latest previous version or 2 versions back. But so far so good. But pay attention, because there's also a sneaky feature of Helm, which is extremely helpful, but that can cause some troubles in these specific situations. So one might think, okay, I have this testing environment, it's a testing namespace. I don't really need, maybe I just want to kind of hibernate my namespace, so just wipe out all my deployments, take everything away. No, not wipe, maybe scaling down some deployments and like leaving some resources there in case I want to scale everything back up someday. I want to save that space, so what do? Yeah, let's delete all the Helm history. And one might think, yeah, great, that's a great idea. And that's what we did too. But beware of the 3-way merge, which is something it's an amazing feature that was introduced by Helm with the Helm 3. And it causes trouble in this particular situation. So this is another lesson that we learned on our skin. So how does the 3-way merge work? The 3-way merge works in a way that when Helm is going to apply and is going to generate a patch of a new deployment of a new manifest, it's going to take a look of the new manifest that is rendered. So you have your template, you have your values, you generate the manifest, and you have this new rendered manifest. And to generate the patch to apply onto the cluster, onto your environment, you're going to have this new manifest, the latest release, and also the live resources. So Helm is going to take a look at the live resources that you have on your cluster and also compare it together with the new manifest and the latest release in the release history. Helm introduced this because without checking for live resources, the users were having some troubles whenever they were trying to tweak something onto the cluster without going through the Helm pipeline. And together with this, there's a 3-way merge, and we can create, finally, the new patch that is going to be applied onto our Kubernetes environment. But what happens if you don't have any history for comparison? So you just have your new manifest and live resources, and then you wiped out all your Helm history because you wanted to declutter your etcd storage. You can end up with the 3-way merge. The 3-way merge is going to get confused. You can end up with a risky patch. And I'm going to show you a little example of a very similar situation that we dealt with. So as you can see, we have the live resource, which has a bad secret. And we want to change this bad secret. We want to remove it in favor of a good secret. And it is a testing environment. So we just have these two. We have the live resource. We have the newly rendered manifest. And we have no Helm history because we decided to wipe it all. What happens here is that Helm doesn't have any reference of the Helm history, so of what it was before. So it's going to check the live resource, it's going to check the new rendered manifest, and it's going to say, cool, let me put both of them. So you're going to end up with 2 volume mounts, and maybe one of them you were trying to delete it, and it doesn't work out. And this can cause, it's not always so bad. Probably you might even end up not even realizing it. But there are some situations when it can cause some problems inside your cluster. So these are the lessons, 3 of the lessons that we learned, scaling up Helm in our big infrastructure. So what are the takeaways from today's presentation? First off, you got to automate. When you're scaling up or pushing the boundaries of your infrastructure, you don't want to do things manually, and you want to ensure that continuous delivery that we are all striving for. And to make sure you to do that, you need some help. And this help is provided by operators, which could be Flux CD, it could be Argo CD, it could be any kind of operator that you want to use to, but they are your friends, so use them to deploy your Helm releases onto your clusters. Let them help you. Second lesson that we learned is that less is more in terms of centralization. So you got to try to centralize as soon as possible if you're thinking about scaling up your infrastructure. And this way, you can not only minimize the traffic, but also make sure that you get the most of your resources. And that you also have a better scheduling, for example, as we saw from the little sneak peeks into our cluster performance. And finally, last but not least, mind that history. So you want to make sure that the Helm history that you have in your namespaces makes sense with the use case of your namespace, with the use case of your environment. And to do that, you got to do some cleanup. You got to shorten this Helm history whenever you can. And this way, you can save up some resources. This is all from today's presentation. I really hope that I left you with some tips and tricks and with some hints or and that I don't know, sharing these lessons that I learned, that we learned in Adobe with you will help you in case you end up in similar situations in the future whether you're scaling up or you're already scaled up and you're trying to make things run a little bit better. So thank you all. And I think we have time for
questions.
Time for questions.
Yep.
Yes. Thank you all for joining. Thank you.